So we talked about inflation almost like an ultimate free lunch. But the free lunch comes with a catch, as I said, and that catch is an uncertainty principle. It turns out that this uncertainty principle is a catch, but it's actually a positive catch. It actually helps us understand the structure of the universe today. So it's based on this idea that physics is not always certain. There's uncertainty to it. So this is actually an experiment people could do by firing electrons on a screen. Just imagine that electrons are being fired by these guns, but you don't know how to aim it, really. So it's a random shot. So you hold your gun, you keep firing it, wherever you can, and you don't know exactly where you're aiming at. So it's totally random. And suppose that there's a screen you would like to hit, but there's another wall between the screen and you, which has two holes in it. And if you keep doing it, you would think, okay, when I fire a shot here, if I fire a gun here, then that would hit the wall. It wouldn't make it all the way to the screen. Only when I fire a shot right in front of this hole, and then the bullet was through the wall and hit the screen. So there will be many shots around here. And if I do the same also down here, if I shoot the gun right in front of the hole in the wall, the bullets end up reaching the screen. So again, we see lots of shots around here, but nothing in between, nothing up here, nothing down there. And that's what you would expect, right? And that's what we thought among physicists too for some 4 centuries. So when physics was believed to be certain, when you fire a shot, you know exactly where it's going to land. But if you actually do this experiment with tiny objects like electrons, so if you look at the microscopic world, that actually doesn't turn out to be the case. So let's watch this video here.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding 2. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biprism, thus creating a uniform distribution without any interference when accumulated. Under such condition do electrons form a uniform distribution. But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
Isn't that incredible? So each time you fire a shot, you don't know where it's going to land at all. It looked totally random to you, I believe. But after a while, you see a pattern emerging. And that pattern is something we physicists can predict. So it's not totally random. There is certain regularity to it. But each time you can predict. So in that sense, physics is indeed uncertain. You don't know exactly what's going to happen for one experiment. But if you keep doing millions of experiments, you can predict the pattern of the outcome. So that's what a microscopic world actually does. And to describe this kind of strange situation, we need something called quantum mechanics, and that is the laws of physics that govern the microscopic world. So even though each electron is a particle, when you shoot it, it lands at a very particular place because it's a point. But when you see this pattern that emerged towards the end of the day, it looks like actually waves. And this is an experiment you can do. So if you have a hose, you shoot water into the pond, it lands here, and there's another guy doing the same thing over there. And each water shot into the pond will create a ripple of waves. It does it from here, it does it from over there. But when the two waves overlap with each other, and this is where you see this fringe pattern, and this is called interference of waves. And the word interference doesn't sound very positive, but what you see is the regular variation in the depth of the wave And that is the effect of interference. So what we saw in the case of the experiment on a previous slide is that, well, we think electron is a particle. But by doing this experiment, we saw a pattern emerging that shows the electron is actually a wave. On the other hand, we always used to think that the light is a wave, but it also behaves like a particle too. So a particle is a wave is a particle, and that's what quantum mechanics is telling us. And strangely enough, when you remember the previous slide, then electron can actually go through two different holes at the same time. If there were only one hole, then electron knows which hole to go through, then there was no possibility of this interesting fringe pattern. So when you throw an electron into that wall, one electron actually passes through two holes at the same time. Very counterintuitive, but that's exactly what this experiment has demonstrated. So if you actually measure the electron along a particular location this way, you do see the fringe pattern emerging. So that's what quantum mechanics does. The laws of physics at subatomic scales has this uncertainty principle built in. You can't predict what happens each time when you do the experiment. But over time, you find a regular pattern. And the only way you can make sense out of this experiment is that you have to accept the fact a particle, like electron, behaves like a wave. Or a wave, like a photon, behaves like a particle. And once you know this, you also learn something else, namely that if electron is a wave, then a wave, when squeezed into narrow space, the wave gets amplified. For example, this is why tsunami caused such a disaster after an earthquake. When a wave comes into narrow valley or narrow bay, it's confined into small space, and the wave is amplified and causes devastation in some parts of the world. So when you're thinking about small space, wave tends to get bigger. And that's exactly what inflation does. When you're during the inflation, and suppose you're looking at an object just next to you, but because the universe is getting stretched out so rapidly, what you thought was your neighbor is now gone all the way beyond some distance. So you feel like you are being nearsighted at the moment. You can only see something which is very, very close to you. So you are kind of confined in a very narrow space. And this constant h we talked about before, that tells you how quickly the universe expands exponentially. And that tells you how big this size of a space is. So during inflation, you're really nearsighted. The only thing you can see are things around you. And because you're confined in a small space, now the wave is amplified, namely there's a big uncertainty. And that's how, during the inflation, these quantum effects show big uncertainties and therefore big wakes of waves. And you can simulate this in a computer. So when you think of the vacuum, you think it's a totally empty, nothing in there, right? But when you do the computer simulation using this quantum uncertainty principle, vacuum is not empty, but it's active. It's like this. So energy is bubbling in and out all the time. So if you're here, you may borrow energy for some time, but you have to give it back. Or maybe you lend some energy to others, you need to take it back again. But as long as everything works out in the end by conserving energy, it's okay. You can lend energy, you can borrow energy, and vacuum, what we think is empty, in doing this actually all the time. So if you put these things together, what would happen? So you have this vacuum, which is lending and borrowing energy all the time. And you also have this inflation that is stretching out the universe so quickly. Now, if you put these things together, you find something really interesting. So universe, we think, was born incredibly tiny. Entire visible universe was smaller than 10 to the minus 26 centimeters, much, much smaller than the size of an atomic nucleus. So in that small confines of space, there was big uncertainty principle at action, and you keep borrowing and lending energies all the time. But suppose you lend energy to somebody else, but then the universe gets stretched so quickly, the person you lent your energy to is now so far away, you're not going to get it back anywhere. Suppose you borrowed energy for somebody else, then the person you need to give my energy back to is now gone forever. Again, you're stuck with the energy you borrowed. So combining uncertainty principle and this rapid expansion of space, you are in the end stuck with small variation of slightly more energy here, slightly less energy here, and you're not going to actually put them back into a smooth space again because you cannot. They're just so far away separated from each other. So that's the way you get stuck with the ripples of energies. Here you have a little more, here you have a little less. Only by a little though. We're talking about 1 millimeter ripple on a 100-meter deep ocean. That's the 10 to the minus 5. It's very tiny. And these ripples keep getting stretched by the macroscopic size because the universe expands so quickly in an exponential way. And that is how we believe that these tiny variations in temperature had been created. So inflation produced these uncertainty principles and little ripples of energies from here to there, and that got printed on the temperature map of the cosmic microwave background. And these small temperature variations have the density variation in dark matter, and dense part accumulates more stuff, and the difference keeps multiplying, and at the end of the day, you see these wrinkles in space-time. So there's the dense part of the universe, there's the sparse part of the universe, and that's how we believe that the structure of the universe was born today. Namely, the fact that we have stars and galaxies today, we owe that back to this quantum noise from uncertainty principle during inflation. So that's a very mind-boggling idea. Well, the structure we see today over millions of light years actually originate from the fluctuation of the vacuum at 10 to the minus 26 centimeters, and that's indeed what inflation does. But how do we know this is true? So if this is true, is there any test we can do that indeed these structures we see today originally came from this microscopic quantum noise? So think about that.